So hello students, we'll continue with unit number 2 and topic number 6, which is computation of float values, critical and semi-critical paths, PERT analysis assumptions, free time estimates, and slack computations. So computation of float values, there are three kinds of floats. The first one is total float. So the amount of time by which the completion of an activity could be delayed beyond the earliest expected completion time without affecting the overall project duration time is the total float. Mathematically, TF total float is equal to latest start minus earliest start for activity I minus j. So, in short, TF total float of activity I and j is equal to L as latest start of the activity I and j minus earliest start of the activity I and j. Next, free float, the time by which the completion of an activity can be delayed beyond the earliest finish time without affecting the earliest start of a subsequent activity is the free float. Mathematically, FF free float of activity I and j is equal to earliest time for event j minus earliest time for event I, that is the activity time for both event I and j. Next, independent float, the amount of time by which the start of an activity can be delayed without affecting the earliest start time of an immediately following activities, assuming that the preceding activity has finished at its latest finish time. Mathematically independent float IF is equal to EJ minus LI minus DIJ. The negative independent float is always taken as 0. Next, event slack. It is defined as the difference between the latest event and earliest event times. Mathematically, head event slack is equal to LJ minus EJ. Tail event slack is equal to LI minus EI. Critical and semi-critical paths. Number 1, critical event. The events with zero slack times are called critical events. In other words, the event I is said to be the critical if EI is equal to LI. Number 2, critical activity. The activities with zero total float are known as critical activities. In other words, an activity is said to be critical if a delay in its start will cause a further delay in the completion date of the entire project. Number 3, critical path. The sequence of critical activities in a network is called critical path. The critical path is the longest path in the network from the starting event to the ending event, and it defines the minimum time required to complete the project. Next, assumptions underlying PERT analysis. The activity durations are independent random variables. The critical paths are independent. The normal distribution can be applied due to the central limit theorem. Assumptions. Activity durations. The expected variance E of V of a critical path is assumed to be equal to the sum of the variances of the critical activities, and hence no covariances between activities are taken into account. Consequently, the activities are assumed to be independent. Critical path. Independency of multiple critical paths is treated in PERT as follows. Next, normal distribution. The project duration is assumed to follow a normal distribution independent of the distribution of the activity duration as a result of the central limit theorem principles. Determining three-time estimates analysis. The three-point estimate is a simple yet powerful estimating time or cost of work items. According to the PMI methodology, it is used in the process groups estimate activity duration and estimate cost. The technique involves three different estimates that are usually obtained from subject matter experts. They are optimistic estimate, pessimistic estimate, and most likely estimate. The optimistic estimate is the expected amount of work or time needed to perform an activity assuming no impediments occur and everything is going smooth. It represents the so-called best case scenario. The pessimistic point is based on the assumption that the opposite was true. It represents the worst case scenario. Although both estimates are referring to the extreme points of the range of expected outcomes, the estimates are supposed to be somewhat realistic. The third point reflects the most likely case. It is the estimation of work or time that is deemed to be the most realistic. One could be tempted to simply use the mean between the optimistic and pessimistic points without giving it a second thought. However, this may not be appropriate for many cases. In practice, it is normally worthwhile to determine the most likely estimate properly, analogous to the other estimation points. The result of the three-point estimating is a so-called triangular distribution of time values or cost amounts comprising of the three estimates. Last topic, slack computations. Calculating the slack time for an activity in a PERT chart is very easy and does not involve any complex calculations. There are two things that are needed to be calculated in the slack time. E as the earliest time when an activity can be started, L as the latest time when an activity must be started. The slack time formula is slack time is equal to Ls minus Es. Calculating slack time for project activities. Alternatively, a slack time can also be calculated as the difference between the latest finish time and the early finish time. Slack time must be calculated for all activities involved in the project. Calculating the slack time is another way of tracing the critical path on a PERT chart. All activities which return a 0 as the slack time are the critical activities. So this is your weekly assignment 6. We have to explain about bar charts, Gantt charts, CPM networks, and PERT analysis. The last date of submission is given here. So that's all for this lecture. You can give your name and enrollment ID in the chat box for attendance. Also, we'll go through a video for your better understanding by IIT Correct. Thank you.
Which is 2-3, that is the activity B. So what we are required to do is to compute the total project duration using the concept of expected times of activities as we have defined earlier, and compute the project durations in the following cases. If the activities are started on their respective optimistic dates, pessimistic dates, and the most likely dates. And then of course we can discuss those results a little bit. So working out the TE and the standard deviations, we find that for activities A and B, we convert this information to this table here. So using these formulae, we calculate the expected times of completion of the activities and the variances. So the total project duration, considering the expected time of the activities, is 23, that is 10 and 13. Now coming to the second part of the problem, which was to say that, well, if activities are completed at the optimistic times, then of course, if we go back to our representation on the time axis and try to say that A is completed in 4 days, then B can immediately follow from here, and in 10 days, the project will be over. However, if they start at the pessimistic dates, the project will be over only in 28 days. That is, this will take 12 days, and then this will go on for 16 days. As far as the most likely dates are concerned, then we are talking of 11 and 14, which is giving us a number of 25. So the project duration obtained by considering the most likely times of activities is 25, is very close to the results obtained by the expected times, that is 23. That is this number here. The time to complete the project if activities started on their pessimistic date, that is 28 days, is also pretty close to this result. So this is 28, and this is also close to this result of 25. However, the project being completed in these two dates, the fact that both of these were outliers only shows that the project can be completed, yes, in 10 days, but we understand that the probability of being able to complete this project in that time is indeed very low. So in the most simple terms, what we are saying is that we become lucky not only once but twice. Not only the activity A is completed in the optimistic time, but activity B is also completed in optimistic times. So we all know the basic probability kind of questions that A and B has to happen in this case. We have to have A being completed in its optimistic time, and we have to have B also being completed in its optimistic time. Of course, there are other combinations that A is completed in its optimistic time and B in its pessimistic time and so on. So that is the kind of range in the time estimation that is important, or that becomes relevant as far as construction management is concerned. So continuing our discussion further, how do we determine the critical path in this method? The critical path is determined by carrying out the forward and backward pass of activities with durations being taken as the expected time of completion. So of course, we take the expected time of completion, and then we use probability concepts to find out what are the probability of completing the project in that time and so on. So expected length or duration of the project, capital TE, is calculated by summing up the expected durations, small TEs, of activities on the critical path. So what we are saying is that if we say that this is the critical path, we are not denying that there are no other paths. There can be other paths, but this is the critical path. So for this critical path, we take the activities on this path and try to find out the expected time of the project using only the expected times of the activities on the critical path. These activities which are non-critical will have to be dealt with separately. And the variance associated with the critical path is the sum of the variances of the activities on the critical path, and we can find out the standard deviation by finding the square root of this variance. So this is the statistical concept which we are not deriving in this course, and I'm leaving it to you to take a look at some of the statistics textbooks and move forward. Now, since the capital TE is the sum of small te's, it is indeed a random variable and follows normal distribution according to the central limit theorem of statistics. The fact that capital TE follows normal distribution can now be used to do these two things. Find the probability of completing the project within a target duration. If there are two activities, we can ask the question that, well, there are some times associated with these two activities, but what is the probability that this project will be completed within a certain time, whatever that number is? That we will see in an example later on, but also we can find the expected completion time with a given probability. Basically, these two questions are just two sides of the same coin. Correspondingly, the standard normal deviate Z is evaluated as TD minus TE upon ST, and this is something which comes in very handy when we are trying to answer questions such as these. So now, to use an illustrative example for PERT, let's say that there is a network which is given here, which is a part of a larger network. So there is a lot of activities here and here, but we are talking only of this part because that is what is our critical path. So for this critical path, the durations are given here for the activities A, B, and C. This is the TO, TM, and TP for all these activities. So what we are trying to find out is the total project duration and the probability of completing this project within 17 weeks. Now 17 weeks, please see, is, if we do a very simple calculation, 4, 4.5, and 6 will give us 14.5. So what we are saying is that if we just take the most likely times, we did that in an example just now, that if we just take the most likely times, it turns out to be 14.5. So what we are talking about is that what is the probability associated with completing this project, not in 14.5 or 15 weeks, but in 17 weeks. So what the probability should be is what we need to calculate. So moving forward, we first calculate the TEs and the ST squares using this formula, and we find out the capital TE, which is the total project duration, by summing up these three small TEs, and we find 15. Similarly, the variance which is associated with the project is the sum of the variance of the activities, which is 1 in this case. So the standard deviation is 1. So we have this calculation carried out. Now with this calculation, we go to the charts and tables relating to finding out how this area is related to the number of standard deviations that you go away from the mean. So if you do this exercise for this particular project, here we have 15, here we have 17, and here we have 1. 17 is our target. We want to find out what is the probability associated with completing the project in 17 days, which is higher than 15, which is the most likely time of completing this project. So this number here, which has been arrived at using the expected times, is 15, and we are trying to find out what is the probability associated with completing the project in 17, and this is the standard deviation. So the Z value is 2, and with this, if we calculate the required probability, we'll find that the answer is 97.7%. So what we can say is that the probability of completing this project in 17 weeks is 97.7%. Here we can say that yes, the capital TE represents that time which has a 50% probability of completion. So with this, we have introduced the concept of PERT. We have introduced the concept of uncertainty in the activity durations. Now suppose instead of 17, we were talking of 13. If you go back to the data given here, the T naught for the three activities is 3, 4, and 4. So the idea is that instead of 15, which represents the 50% probability of completion, we are talking of going -2 here at 13. So what will be the probability of completing this project in 13 days? Of course, there's a finite possibility because the optimistic times associated with these three activities is indeed less than 13. This is something which I'm leaving to you as a food for thought. You try to do this example on your own, and I'm sure you'll get the answer very quickly. And I hope that you now understand how to handle these concepts and be able to talking of what is called crashing of a network. Now, what is crashing? Construction projects involve considerable amounts of expenditure in terms of time and money. Activities in the projects have to be scheduled such that they are completed with the minimum time and cost. In our earlier discussions, we have seen that both time and cost are largely dependent on the resources allocated to the individual activities in the project. One of the important features in network analysis applied to construction management, like CPM, is that the duration of an activity can be reduced to a certain extent by increasing the resources assigned to it. Now, in this lecture, let's look at the concept of reducing the project duration by reducing the durations of critical activities in the project by increasing the resources allocated to them. What we had said last time, and I'd like to reiterate that today, there are two kinds of activities, let's say, critical and non-critical. By doing reallocation of resources, leveling resources, we try to rationalize the resource deployment over the period of time, and that is done with non-critical activities because the duration of the project is governed by critical activities. So now the discussion today is there a possibility of reducing the overall duration of the project? Now, in order to reduce the duration of the project, obviously it's not important to concentrate on the non-critical activities. Obviously, we must concentrate on the critical activities. Meaning thereby that if we want to reduce the duration of critical activities, obviously there will be a requirement or a commitment of additional resources, which will cause additional expenses. What has to be seen is whether this additional expense of resources can be justified in terms of the benefits that may accrue to the contractor by finishing the project early. That is something which is relevant because as far as the contractor is concerned, the project cost has a direct cost and an indirect cost and so on. So we have to see the overall perspective of balancing the additional resources, of balancing the expenditure in the additional resources and the benefits accruing therefrom. So that basically is the essence of what we will talk about today, and that is what is called crashing of network. Now, what are the components of total project cost? One component is obviously direct cost, which comprises of expenditure that is specific to a project, that is cost of materials, labor, and equipment. Indirect cost includes expenditure like tariff for infrastructure facilities, rent, and so on. Now, cost-time trade-off is what we talk about really. The analysis of the interrelationship between the time and cost of a project in order to minimize its cost and duration is called the cost-time trade-off. This picture here is a schematic representation of what goes on. If we try to reduce the project duration, our direct cost increases, but our indirect cost decreases. So the total cost, which is essentially the sum of the direct cost and the indirect cost, that is what has to be seen. So it will reduce up to a certain point in time and then start increasing again. So we should be targeting at getting to this duration of the project. In other words, by reducing the duration of individual activities, the total cost of the project can be reduced to an optimum level. Now let us technically define what is crashing. Expediting an activity to an earlier time by mobilizing more resources, committing more resources to it, is known as crashing. Now let's look at an example to explain this concept. Consider a project having 6 activities, A, B, C, D, E, F, and the network of the project along with the durations of the individual activities is shown here. The cost of crashing individual activities, it could be in any units, it's given in Indian rupees here, is shown in the table given below. Now this is the table. Determine which activity should be crashed first in order to reduce the project duration. So suppose we have this project which has 6 activities and these are the durations. Let's say that is given in days, and this table gives us the cost of crashing for 1 day. So if we want to carry out activity A in 3 days, it is possible, even though it is 4 days here, it is possible to do it in 3 days, provided we are able to mobilize additional resources of 4,000 rupees. Similarly, activity E instead of 6 can be done in 5 days, provided we are willing to spend another 1,500 rupees. We must remember that at the end of it, it is not possible for any activity to be infinitely crashed. That is, we cannot say that if we are willing to increase the commitment of resources indefinitely, the time can be reduced indefinitely. This cannot be done. There may be minimum times for any of these activities beyond which, no matter how we crash it, it will not work. So there is a minimum time which is required, there is a reasonable time which we are willing to give, and beyond that reasonable time, yes, it is possible to reduce it to that minimum time by putting in additional resources. So this is the backdrop of carrying out this exercise. So once we have this information listed with us, which is the cost of crashing for 1 day for the different activities, obviously it makes sense to begin with the activity which requires the minimum amount of cost. So we should do that activity first, which involves minimum additional commitment of resources. The second part of it, the discussion is that activity critical? Will really making that commitment help as far as reducing the project duration is concerned? That will happen only when the activity is critical. So the first thing to do perhaps is to find out which are the critical activities and then try to see what are the resources required if we want to crash those activities. So let's move forward and we do the network analysis. We try to find out that the paths in the network AD, BE and CF, these are the 3 paths in this network comprising of activities AD on one side, BE on the other, and CF is the third. And the critical path is BE. This takes 6 and 6, 12 days. This takes 10 days and this is 9. And we are looking at the maximum of this, and therefore the critical path is BE, which is 12 days long. So this project with the given information can be completed in 12 days at a certain cost. Now let's try to see how we will use this information on crashing. The first question to be asked is which activity should be crashed? From our analysis given here, the duration of the project is governed by the critical path BE, and since the cost to crash E by 1 day is lower than that of B, activity E should be crashed first. So we are looking at E is critical and B is critical. To crash B, it requires 2000. To crash E, it requires 1500. And therefore, it makes sense to crash E first and then see how things change. Only to reiterate, even if any of the non-critical activities A, D, C and F is crashed, the project duration will still remain 12 days and it makes no sense to do that. Now let us try to formally define what is called the cost slope of an activity. The extra cost in expediting an activity to reduce its duration by unit time is called the cost slope of that activity. That is given by crash cost minus normal cost divided by normal time minus crash time. That is the cost slope. In fact, in this table, when the cost of crashing for 1 day was given, what was essentially given is the cost slope of all these activities. Because what we mean by this is that this is the cost that is incurred for crashing that activity by a single day. And obviously, from the given set of activities, the activity that has the minimum